Hello everyone. Today we are going to be talking about calculus, but not f of x calculus. This time we're going to be talking about polar calculus, where the radius or the distance from the origin is a function of the angle it makes with respect to the x-axis. Well, the x-axis is still there. It's just now in terms of r and theta. So let's go ahead and take a look at this function right here. R of theta is equal to sine of 2 theta from 0 to pi over 2. This is just a domain restriction in the polar world. So we only have this one pedal-like function right here. So we are asked to find these four things. Let's start off with A. Find the slope of a tangent line to r of theta at theta is pi over 4. So we need to find the slope. Well, the slope of the tangent line, we know in Cartesian calculus, or y as a function of x calculus, we know that this is dy dx at theta is pi over 4. But how do we get y and x when we're in terms of r and theta? Well, there are simple conversion formulas. Recall from trigonometry that y is equal to r sine theta and x is equal to r cosine theta. So we can actually apply these formulas to convert from polar world to x and y world, or Cartesian world. So y is equal to r sine theta. Plugging in the function we have for r is going to give us sine 2 theta sine theta. And plugging in for x is going to give sine 2 theta cosine theta. Now what we need to do, let's go ahead and differentiate both of these functions with respect to theta. So by doing so, we get dy d theta. And all we have to do here is just apply the product rule. So by applying the product rule, we get sine 2 theta cosine theta plus 2 cosine theta 2 theta, just based on the chain rule, times sine theta. And then doing the same for x as a function of theta, we're going to get dx d theta. That is going to be equal to, let's go ahead and differentiate sine 2 theta first. So it's going to be 2 cosine 2 theta cosine theta minus, because we're differentiating cosine, and the derivative of cosine we know is negative sine. And then we minus sine 2 theta sine theta. So to get dy dx, let's go ahead and break down dy dx. So we know dy dx can be written as a fraction. So if we multiply both the numerator and the denominator by 1 over d theta, this gives us dy d theta over dx d theta. And that's exactly what we have up here. So let's go ahead and substitute what we have up here in for dy dx. This gives us sine 2 theta cosine theta plus 2 cosine 2 theta sine theta over 2 cosine 2 theta to cosine theta minus sine 2 theta sine theta. Alright, and now whenever we see a theta, what we need to do, since we're evaluating it at pi over 4, when theta is pi over 4, we need to plug in pi over 4 for theta. So, dy dx at theta is pi over 4. This is going to give us sine of pi over 2 times cosine pi over 4. Notice that this is pi over 2 because 2 times pi over 4 is pi over 2, plus 2 cosine pi over 2 sine pi over 4. All divided by 2 cosine pi over 2 cosine pi over 4 minus sine pi over 2 sine pi over 4. So we can actually go ahead and do a little bit of cancellations, because if you notice, cosine pi over 2 is 0. So this is going to cancel and this is going to cancel. So, and sine of pi over 2 is 1, so we can get rid of this and this. And if you notice, we are left with negative cosine pi over 4 over sine pi over 4. And we know that this is cotangent pi over 4, or negative cotangent pi over 4, and we just get negative 1. So if you notice, this is saying that if we look at, let's say this is pi over 4-ish, if we draw the tangent line to this, or the line tangent to this graph at pi over 4, we will get that this slope right here, this slope is negative 1. That is essentially what this means. So that's part A. Let's move on to part B now. Find the maximum height of our theta, or of theta. So the maximum height is basically saying, imagine this was on the xy plane. If this was on the xy plane, then what would the maximum y value of this graph be? Let's go ahead and take a look. So, in order to find the maximum height of our theta, what we need to do is we just set dy dx equal to 0, because we know that we get maximums and minimums from whenever there's a horizontal tangent, which is when dy dx is 0. So, whenever dy dx is 0, you'll notice that this right here is pretty much irrelevant, because for a fraction to be 0, the numerator must be 0. So, sine 2 theta cosine theta plus 2 cosine 2 theta sine theta, this has to equal 0. So what can we do to actually simplify this? So 2 sine theta cosine squared theta plus 2 times 1 minus 2 sine squared theta sine theta, this is equal to 0. We can actually go ahead and work this out if you want, but that's not necessary. In the end, I believe the angle that we get, theta, is equal to the inverse sine of the square root of 2/3. And if we just go ahead and plug that into what we have here, this is going to be equal to y equals sine of 2 times the sine inverse of the square root of 2/3 multiplied by the square root of 2/3, because sine and inverse sine will cancel. So this right here is the exact form of our answer. And this is actually just the maximum value that we will get. So yeah, that pretty much concludes this portion, or the derivatives portion. Let's go ahead and move on to areas, or integrals, if you will. So, this is saying that we need to find the area of region R. Now, be careful here, because if you notice, this is a polar function. We can't use rectangular approximations for areas. What we do actually is we go ahead and make circular sectors with an angle theta, or a angular displacement delta theta. So if you go ahead and draw all of these angles, or just something that looks like this, you'll notice each of these areas, we'll call this area initial. So we know that the area is just the sum of all of the area initials from 1 to n, or whatever. Or no, it's not initial actually, it's just a sub I. But what is a sub I? Recall that the area for a sector of a circle, because these are all sectors of circles, this is equal to the sum from I going from 1 to n, where n is the amount of circular sectors, of 1/2 r sub I squared delta theta. Now, to properly approximate the area of this pedal, or this polar function, we limit delta theta to 0. So area is the limit as delta theta goes to 0 of 1/2 times the sum going from 1 to n of r sub I squared delta theta. So this right here is the limit. This right here is actually the limit definition of an integral. So what we do is we get a is equal to the integral from a to b of 1/2 r squared d theta, because this delta turns into d because we're limiting it to 0. So Let's go ahead and take a look at this sine 2 theta and plug it into this integral formula. This is going to be the integral from, notice, our domain restriction is 0 to pi over 2. So these are going to be our limits of integration. So this is going to be 1/2 sine squared 2 theta d theta. So if you go ahead and break down this integral, what you actually need to do is we need to do a bit of a u substitution. So if we let u equal 2 theta, du, we know that's going to be 2 d theta. So d theta is 1/2 du. And you know that we have to change our limits of integration. So this 1/2 right here is actually going to become 1/4, first of all. And these limits of integration, we just plug in our original limits of integration into the expression we have for u. So 2 times 0 is 0. 2 times pi over 2 is just pi. So this is going to be sine squared u du. Now, how do we integrate sine squared? Well, recall that this cosine 2 theta identity is 1 minus 2 sine squared theta. If we go ahead and do some algebra, we get cosine 2 theta, 1 minus 2 sine squared theta. And if you can just solve for 2 sine squared theta, you get that this is equal to 1 minus cosine 2 theta. So dividing both sides by 2 gives us 1/2 1 minus cosine 2 theta. So you notice this becomes 1/8 times the integral from 0 to pi of 1 minus cosine 2 theta d theta. And now we can just evaluate this integral. So this becomes 1/8 theta minus, we need to do the reverse chain rule for this. So we have this 2, and we need to have a 1/2 in front because it's the reverse chain rule. We're just dividing by what's inside here. This is 1/2. The antiderivative of cosine is sine. This is going to be 1/2 sine 2 theta evaluated from 0 to pi. And as a result, we get this is 1/8 pi minus 1/2 sine 2 pi. Sine 2 pi is 0, sine 0 is 0. This is just going to be pi minus 0. So the answer is this region right here is pi over 8. All right, that's part C. So lastly, what we need to do, find the average distance, a point of r theta, a point on r theta, this should say on r theta is from the origin. So this is basically saying how far is some point right here, let's take this point, how far is it from the origin? Well, this right here is actually just our r value. So what we're really doing is we're finding the average value of this polar function. And we know that from Cartesian calculus, the formula for average value is just 1 over b minus a times the integral from a to b of f of x dx. And well, in this case, our average is exactly the same thing. So let's just go ahead and plug in our limits of integration. So this is going to be 1 over pi over 2 minus 0 times the integral from 0 to pi over 2 of sine 2 theta d theta. So this is going to equal 2 over pi times the integral from 0 to pi over 2 of sine 2 theta d theta. And if we go ahead and evaluate this integral, the antiderivative of sine is negative cosine, and we need to have a 2 or 1 over 2 out front because of the reverse chain rule. So this is going to be 2 over pi times negative 1/2 cosine 2 theta evaluated from pi over 2 to 0. So these 2's right here are going to cancel, and we can just go ahead and bring the 1 out front. This is negative 1 over pi. Cosine pi is negative 1, and cosine 0 is 1. This is going to be negative 1 minus 1, and so the average distance is 2 over pi. And we can actually also think of this average distance in a different way. Let's say we were to draw a circle, all right? So this circle right here is the function r is equal to 2 over pi. So if we go ahead and take the area of this quarter of the circle, this area right here is also going to be equal to pi over 8, or the area of region R. Sorry, the area of region R, yeah. But yeah, with that concludes this video on polar calculus, and this is Akil from Auxin Academy signing off, and I hope to see you in future videos.